Welcome back to the course Modeling Combustion with Answers Fluent offered by ADAR Systems. In today's class, we will discuss about premixed combustion model. So let's begin the class. So what is premixed combustion model? So we have seen earlier the non-premixed combustion model, and compared to it, premixed combustion modeling is very much difficult and complex because the premixed combustion occurs as a thin propagating flame that is stretched and controlled by turbulence. So turbulence is the thing which controls the combustion and propagation of premixed flames, and so the essence of modeling this kind of combustion lies in capturing the turbulent flame speed. So the main focus for this premixed combustion model is to simulate and to understand the laminar flame speed as well as the turbulent flame speed. So just like non-premixed combustion model, here in this model, one of the important parameter which holds the entire thermochemistry is the progress variable. In non-premixed combustion model, it was the mixture fraction. Here it is the progress variable. But both of these factors are very different from each other. So wherever C equals to 0, that means that unburned gases are present there, and wherever C equals to 1, that means burned gases are present there. So the flame which occurs in premixed combustion is in the range of C equals to 0 to C equals to 1. So this helps in visualizing and putting our boundary conditions very specifically so that a premixed combustion model can be simulated. So some of the key features of this model are: this model offers two types of flame speed determination models, that is Zimot flame speed model and Peters flame speed model. So for this model to ignite the premixed mixture which is present, we can use the spark ignition model. Then one more thing which is important in modeling premixed combustion is that here we have to specify each and every unburnt physical property for the unburnt mixture. So unburnt density and unburnt temperature are some of the properties. Other properties we will see in detail in upcoming slides. Then we discussed about defining the progress variable C, and the last one, that these models have three options, that either we can model our premixed combustion using C equation, G equation and extended coherent flame model. So these three models are different, but overall the aim or the motto to model premixed combustion is the same. So some of the limitations for this model are: this model does not work with density based solver. Also pollutant models cannot be used with this model, and then this model can be used only to model deflagration flames, that is subsonic flame. We cannot model detonation using premixed combustion model. So this was complete overview for premixed combustion model. Now we will see what all are the steps involved in modeling premixed combustion. So these are the steps which will help us model our premixed problem using Answers Fluent in a very better way. So we'll discuss each of the steps progressively in upcoming slides. So coming to the first step, that is enabling the premixed turbulent combustion model and its related parameters. So after defining the turbulence model and energy model, we have to come into species and we have to enable the premixed combustion model, where we can select what energy treatment we want to use, just like the other models, that is adiabatic or non-adiabatic. Then we can select what premixed model we want to use, that is C equation, G equation or extended coherent flame model. So based on whatever we select, we can change our turbulent flame speed model from Zimot to Peters. So when we select this Peters flame speed model, we are able to modify the model constants or some of the main parameters which defines the Peters flame speed model. So this option is only available for Peters flame speed model. So next, for the second step, it is defining the physical properties of the unburnt materials in the domain. So after defining the models and everything, we have to specify the unburnt physical properties like laminar flame speed, critical rate of strain, etc. So when we are selecting adiabatic or non-adiabatic, these set of parameters will change accordingly. We have to specify these parameters based on the standard conditions. To get these values of properties, we can refer to some standard combustion handbooks. So the next third step here is setting the value of progress variable at our flow inlets and exits. So as we have seen that there will be a flame propagating. So wherever C equals to 0, that means an unburnt mixture, that is where the pre-mixed air and fuel mixture is present at inlets. So we will define C equals to 0 at inlets and C equals to 1 at our exit, so that a flame is propagated into this range from inlet to outlet. So the next step, the fourth step, is initializing the value of progress variable. So even after giving some boundary conditions of C equals to 0 and C equals to 1, it may happen sometimes based on the problem that the flame may blow back into the stabilizer. So a very good practice here is to patch the progress variable based problem. That is, upstream we will patch C equals to 0 and downstream we will patch the progress variable as C equals to 1. So this may reduce any blowing back of the flame problem when modeling premixed combustion. combustion. So this can be done into solution initialization, and there we have an option of patching. So after patching the value of progress variable, then we have to start our simulation, and then we have to perform post processing. So even here there might be some convergence issues. So same strategies which we have used for earlier two models, we can use the same strategies to make our solution convergent, that is by changing some of the under relaxation factors, performing a code flow simulation earlier and then hot flow. So the post processing parameters which we can use for premixed combustion model are shown below. So we can generate graphical plots or alphanumeric reports of the following terms when we are done with premixed combustion model. So now we will see a demonstration of premixed combustion modeling with an example where we will discuss step-by-step procedure for pre-processing, solution and post-processing. So let's begin. So for this demonstration of premixed combustion modeling, we're going to use a 2D tube which is shown below. So this is 40 centimeter long tube with 1 centimeter height. So we're going to use this as our problem. So pre-mixed mixture of methane and air will be entering into this domain, and then we will be igniting this mixture using a spark which will be located at the entrance. That is, it will be located at the inlet. So these are the spark parameters which we're going to set into ANSYS Fluent, and we will see how we can do it. Next here we can see that 1 mm of region is highlighted here. So this is nothing but, as we discussed, that we have to patch value of progress variable c equals to 0 where we have unburnt mixture. So at inlets we will have unburnt mixture which is entering the domain. So we will use cell adaptation option in ANSYS Fluent to patch c equals to 0. So we'll see how we can do it. Next we have this unburnt physical properties which we have to enter in ANSYS Fluent during the simulation. So these properties are for methane air mixture. I have collected these values from one of the chemistry solving software. It is called as GASIQ. So in GASIQ you have to specify your reactants which you're going to use for your simulation and their mole fractions. So once you input these parameters, you will get all the unburnt and burnt mixture properties. So same way I have calculated using GASIQ, and then we have the spark parameters. So what we will do is that for the pre-mixed mixture to enter the domain, we will use a steady state calculation. That is, initially we will do a steady state simulation in which the reactants will be entering into domain. Then to ignite this mixture, we need spark model. So one condition for spark model is that it works only with transient simulation. So after the mixture has entered completely into the domain, we will switch to transient simulation and then we will ignite the spark. Then we will see how the combustion is initiated and how the flame propagates downwards. So we will see this step-by-step procedure in ANSYS Fluent. So let's go to Fluent GUI. Okay, so here I have imported this 2D tube which we have seen in our problem definition. So first check, that is quality check. We'll go for check, then report quality. Then I'll show you what parts actually we're gonna deal with. I'll close this interior surface, wall surface. This one, display. So this is our geometry we'll be using. So this is inlet, this is outlet, this is the symmetry part. We won't be modeling the complete geometry. So we will be using symmetry here, and these are the walls. So I'll close this one. Then as discussed, we will do steady state simulation. So we will go into models, and here one thing I will show you is that energy equation. I am switching it on now. We'll see how this energy equation gets turned off automatically when we go into premixed combustion model. So first we will change this viscous model from SST K omega to K epsilon. So I'll go with OK. Then we have to go into species, then premixed combustion. So here we are using adiabatic energy treatment. So our problem is adiabatic. So we are using this. Then we have flame speed model as Z mode. We have to apply unburnt physical properties, so we have to give those, like OK. Now we can see that in species premixed model only reactor network is on. So if we were dealing with transient simulation, then there would be a spark model entering here. So we will check that later. We will go into materials now. So we can see that only air as fluid and aluminium as solid is here, fuel as well. So for this simulation we will use Fluent database. And we have to search for methane in this. Okay, methane is here. We have to select this one. Then simply we have to select copy. So this methane will be copied into materials. We'll close this window. So here we can see in fluid we have air as well as methane. So we have to change the properties of methane here. So we have to import the properties which I showed you earlier for the methane here. So density, we can see that the premixed model will be used. For viscosity, this constant value. We can even change this. Right now we will check what values we will be using. So viscosity, we have to use 1.80 e to the power minus 5. So we have to change this value slightly. We will change it to 1.80 e to the power minus 5. Then adiabatic unbound density is 1.226. We will change this to 1.226. Adiabatic unbound temperature is nothing but 300 Kelvin. It is maintained here. This we just have to change the adiabatic burn temperature, which will be 2300 kelvins. Then it is unburnt thermal diffusivity. So we will check for the diffusivity value. It is 2.01 e to the power minus 5. We'll go and change this to 2.01 e to the power minus 5. Laminar flame speed is 0.2, the default value. Critical rate of strain 1 e to the power plus 8. So 0.2 and 1 e to the power plus 8. So this has been defined for methane. We just have to click on change create. Then properties are defined now for methane, that is unburnt mixture properties are defined. So we will close this window. So you can see methane and air is there. Then we have to go into boundary conditions. We'll go for zone type. Inlet will be using as velocity inlet. So the velocity which we're gonna deal with is 0.8 meter per second. So the flow will be entering with 0.8 meter per second velocity. Then species, remember that species which are present at inlet, that is unburnt mixture. So progress variable value here will be 0. So to go and click OK. Outlet will be using pressure outlet. Remember the main thing which we will be changing here is in species, that is the progress variable will change to 1, because at outlet mainly the burnt mixture will be coming toward. So we'll go for OK. Then symmetry, already symmetry has been defined. We don't have to do anything. Wall is there. Interior is defined. So boundary conditions are done now. Then we have to go into methods, then changing it to simple, then changing this turbulent kinetic energy from first order upwind to second order upwind. So this change is done. Controls here right now we don't want to do anything because we are not doing any big or highly complex kind of premixed combustion we are not dealing with. So we won't be using these options. Then initialization, standard initialization, compute from inlet, absolute values, then initialize. So the problem has been initialized. So we will go into run calculations. Remember first we are doing simple steady state simulation. So we'll go and change the number of iterations to say 100 I'll be using here. Then main important thing, that is we have to write this case file. So I will quickly go and I will write this case file. Remember that we have to specify steady and transient when we are saving this case files, just to remember, because other time when we'll be reading this case files back to extract some solution details, then we will need to understand that which case file we want to use. So we will save it as premixed steady. So the case file is getting saved. Next we have to go for calculate. So the solution has completed. We'll go for OK. Then we have to save this data file. So write data in the same place where you have saved your case file, you have to save it there. So data file has been saved. So now what we have to do, we will go into graphics and we will check that any species or any changes has happened or not. So we will see for pressure values. So pressure, we can see that there is little change happened. Then we will check for velocity. So velocity we gave 0.8 meter per second. It has increased little bit. Then for premixed combustion, we'll see for progress variable. So we have defined progress variable C equals to 0 at inlet, C equals to 1 at outlet. But here we see that there is no change at all. This is because it is completely filled with unburnt mixture here. There is no flame, there is no combustion here. So we have to go and we have to ignite this mixture using spark ignition model. So we can use spark ignition model once we turn the time from steady to transient. So we'll be changing to transient simulation now. Then we will go into models, and in models under species transport we can see there is spark ignition model which is in off now. So we'll go and we will define these conditions. So here we have to set our spark parameters. So we have to go in our word file and we will check for the spark parameters. So spark radius is 1 mm. So we'll specify here 0.001. Energy is 0.006 joules. Duration it will be for 0.003 seconds. Start time will be 0.01. Then X center, as we saw earlier, that spark is located at 1 mm distance. So X center will be 0.001 meter and Y center will be 0.005 meter. So all the spark parameters has been set now. We have to go and click OK. Then we have to apply, and we have to make sure that this we have enabled. Then we'll close. Then rest all we don't have to specify here anything. One thing we have left here to do is we have to patch our value of progress variable c equals to 0 at inlet. So how we can do is we have to go into patch, and right now here we see that there is no region present here. So we have to create new region. So what we will do is we will go here and we have to select adapt option. So here we can see this adapt option is there. We have to go into refine and coarsen. Here cell registers, new region. So here we have to specify a region which we want to visualize. So x minimum will be 0 and x maximum will be the 1 mm distance which we will be using. So 0.001. Y minimum will be 0 and y maximum value, that is the tube height is 1 centimeter. So it will be 0.01 meter. So we can even display this region which we have selected. So we'll go for save display. So here we can see that this region which I showed earlier in our image, so this 1 mm distance, it has been traced, and this will be used for our patch region. So remember the name, that is region 0 we are saving. So this region will be using for our patch. So click OK. Everything is done. We'll minimize this window here. Then we have to go again into patch. So here we can see, so progress variable, value 0, region 0, patch. So this has been done. Then what we have to do is that when the simulation is running for each time step, we want to save contours or images of the static temperature, velocity, etc. for each time step which it is getting calculated. So once the simulation is done, we can directly visualize these results using an animation. So for that, what we can do is that we have to go into calculation activities. Here we can see that solution animation is there. You have to select it. You can change the name if you want. You can change a record after every one time step or other parameters, iteration, flow time, anyhow you want. Then you have to change this storage type to JPEG, so you can have every single picture of the time step change. You have to change the location. You select the folder where you want to save, then window, at what window. Then we have to select what contour you want to see. Contour which we created earlier, it will show this contour one. We can use preview. We can see what it is showing. So here it is for progress variable. So what we want is we want to contour for static temperature. So we will go into new object and contours, and in premixed combustion there is progress variable and there is static temperature. We'll go for save display, and we can see that it is contour 2. So we have to go and select contour 2 either other than contour 1. Right now we can see that this is minimized one. So what we can do is we can zoom in, and then we have to place it where how we want to see. Then we can use active option here. So this view will be set. Then what we can do is we can go for OK. Then we have to go into calculation activity, so that after each time step a data file is saved. So auto save entry at each time step. So we'll go into edit and we will give the path where we want to save it. So first we have to save case file before doing this. So we'll save the case file and then we will come back to this place. So what we are using, the time step size will be 0.01. Then number of time steps is 15. That is, we're gonna simulate it for 15 milliseconds. Then number of iterations for each time step will give 30. So everything is done. We have to go and we have to write our case file. So write case, and here we just have to change this from steady to transient just to make it more easy. So save this case file. So once the case file is saved, we can again go back to calculation activities, edit, and give the path. You can select the transient from here. So it will be saved based on the time steps, and click OK. Just go back to run calculation and click calculate. But before clicking the calculate option, there is one more thing which we can use here is the titles visibility. So this will help us to visualize the time variation which is happening. And one more thing one have to be observing after starting the calculation is that when console, it will be clearly showing the spark activation in between. So we will see that we have given that at 0.01, that is when the simulation starts, the spark has to be ignited for 0.003 milliseconds. So we'll see how this works. We'll go for calculate. So here we can see that the spark active has come in the console, and we can see how the residuals have been changed once the simulation has started. So we'll see for the 30 equations how it goes, and how again it starts with the first iteration where spark will be again on. So here we can see this temperature contour, and we can see spark is active. So same way it will go for next 15 time steps, and we can see both of the things. So here we can see the temperature change, how the temperature is changing for each and every time step, and then we can also check how it is getting saved automatically in our folder where we have specified. So again, for 1 more second, Spark will be active. So it is done. So we can check that the time step is now 3.0. So it will go for 4.0 e to the power minus 2. So the spark has initiated, and we can see that for 3 times the spark has ignited. This is the first initiation, then second, and then third. So 3 times the spark has ignited. Okay, so here we can see that the calculation is complete, and this is the final temperature contour for 1.5 milliseconds, and these are the scaled residuals. The calculation is complete, and then now we have to do some post processing. So I'll close the setup and the solution tabs here. So we will just go and check for the temperature value which we have attained. So first we will check for temperature, that is temperature value which it has attained is 2000 Kelvin. We can see how the flame has begun, and when the new air and fuel mixture is entering, it is getting ignited after some time, because now we don't have any spark here. So whatever the flame is already present here in the domain, it will ignite the incoming mixture as well. So this way the combustion will be continuous in happening, and the flame has reached to the outlet in this manner. So we will check for progress variable as well. So we will go for the second contour which we plotted. So here we will check for progress variable as well. So progress variable and temperature won't be much different. So maximum one has reached. So we'll close this. Then what we have to do is that the animation which we created, we can go and we can check this animation here in this playback option. So we'll just go here playback. So from here it will be very clear for us to see that how the temperature has varied and how spark has initiated. So we'll just play this. So it will be very fast. So what we have to do is we have to come here and we have to reduce the playback speed. Then you have to play. So for each and every time step we can see this, we can see a flame coming out from the spark region, and then it is propagating towards the outlet. So whatever the fresh fuel and air mixture is entering the domain, it is getting consumed and it is moving downstream. So this way it has been calculated. So what we can do is we can also save this file directly. So we will go into write record format, then we'll go to NPEG, that is video format, then we will go to write. So it will automatically write in the folder where these all animation files were saved. So once it is done, it will show us. It will also show the location where it has been saved. So this is done. We can also go and check into the folder. So here we can see that these are the image files. So we can individually go and check the image files here. So here it will be clear with the time as well. So this we can either we can collect all these images and then we can club them together and make a video, or we can do it with the ANSYS Fluent how we did just now. We will also check for some vectors here. We will see how the vectors look for this problem. So we need to increase this ratio here. We will do it 10. So here we can see I have to reduce it little less. Yes, so here the mesh is fine. So that's why we were getting a very big, I'll go with 1. Okay, so in 1 it is very clear and visible. Then here we can see that the flow is moving towards the walls at the upper region, because the flame is happening there, and whatever the fresh air and fuel mixture is entering, it is getting consumed within the flame. So these are the velocity vectors. We'll close this one as well. We can go into reports. We can check for surface integrals. We will go and we will check for mass weighted average. We will check pressure for inlet. We'll compute. So this much is the pressure. And we'll compute for outlet as well. So we'll get to know the change happened. So this pressure difference is there. We'll check for progress variable. So progress variable at inlet is very less, and progress variable at outlet has reached 0.2. Since this is at 1.5 e to the power minus 1 second. So here we can see that it is not completely reached to 1 value. We can go and check for temperature as well, static temperature. So for outlet, mass weighted average temperature reached is 654 Kelvin, while at inlet where we specified is 300 Kelvin. Also here one of the important things we need to check is the turbulent flame speed. So we'll check turbulent flame speed at inlet. So inlet it is 0.2, and we'll go for outlet. Outlet we will check it has reached to 0.5. Then we will check for velocity. So velocity at inlet we will check where we specified 0.8. So it is 0.8, and on outlet we have to check. So it has reached 6.7 meter per second. So such a huge velocity difference has been created because of the combustion wave, which is initiated in the domain using spark mode. So to close this, next we will go for some XY plots. So we'll go into XY. We will check for X value, axis will be 0, Y axis will be 1. We'll be plotting velocity here again. So we'll plot velocity for inlet. We'll see how the velocity is there. So we specified 0.8. We'll check for the outlet. So when we compare this inlet and outlet velocities, we can see how they are varying at different locations. I will check for temperature as well. So we'll go into, okay, first we will check for progress variable. So this is how progress variable is reached. So this, in this region, combustion is happening because at inlet there is zero value, that is unburnt mixture is coming, and then it is getting consumed and a burnt mixture has been represented where the C value, the progress variable value, which is not equal to 0. Then we will go and check for temperature as well. So temperature plotting, if we do for inlet and outlet the same way, then we'll check for turbulent flame speed comparison. So this is how the turbulent flame speed is varying in the region, in the domain for inlet and outlet. So this was all about premixed combustion modeling in ANSYS Fluent. So we have seen the step-by-step procedure and how we can use steady state simulation and then switch to transient simulation where we have to use spark ignition model. So this way it helps to solve some of the major complex combustion problem where premixed combustion is involved. What are the things we studied in today's class? The summary for the class is that we've seen premixed combustion modeling is difficult than modeling non-premixed combustion model because the flame occurs as a thin propagating flame which is controlled by turbulence, and thus making this as the motto or the focus of the model that it has to simulate the laminar flame speed as well as the turbulent flame speed. Then we have seen that progress variable is the parameter which holds the entire thermochemistry of the model and helps in defining the burnt and unburnt mixture in the domain. So this model offers two flame speed models, that is Zimot and Peters flame speed model. So based on what condition we are dealing with, we can select a turbulent flame speed model. Then we have seen that we can use spark ignition model along with premixed combustion model to ignite the premixed mixture which is present at our inlets. Then we have seen some of the disadvantages of the model, that pollutant models cannot be used along with it when it does not work with density based solver, and only deflagration flames can be modeled. Then lastly, we have seen step-by-step procedure for premixed combustion modeling using an example for ANSYS Fluent. So the references for today's class are present here. In next class, we will discuss about partially premixed combustion model. Thank you.